Okay, we're going to be talking about logarithmic functions, the graphs in this section. And it says, first off, let's start out with the basic logarithmic function is f of x is equal to log base b of x, where b is the base of the function. It says here a logarithmic function is the inverse of an exponential function. Now let's again explain what we mean by that. Inverses is when we switch our inputs and outputs. We switch our x's with our y's. So if you were to actually take this function here, switch your y with your x, you would get x equals 10 to the y power. That would be the inverse of it. Now, how would you write that in a better form? How would you solve for y so that we could graph that? You would write it as a logarithm, and when you did, you would get y equals log base 10 of x, which is what this is. So these two functions are inverses. If you don't remember, also, when you're dealing with the graphs of inverses, they are mirror images across the line y equals x. So if you were to graph 10 to the x power, 10 to the 0 is 1, 10 to the first power is up here at 10, 10 to the negative 1 is like a tenth. It looks something like this. It's an exponential function, and we did a whole section on that. Had an asymptote line at y equals 0 and a y-intercept at 0, 1. So if you were to look at the graph of this one now, it would actually cross at 1, 0. And the other points, since 0, 1 was on this, 1, 0 is on this. Since 1, 10 is on this function, then 10, 1 would be on the inverse function. This inverse function would look something like this. It looks a logarithmic function looks a lot like that 10 to the x power. It's just a mirror image across that line y equals x. And we can actually use this fact to graph these. To graph a logarithmic function, you can use the inverse exponential function. Then invert the values, because we know we don't want to graph the inverse, we want to graph the original. So we can find the values of the inverse, invert them, and then graph that to actually graph like here, y equals log base 3 of x. Let's go through those steps. So instead of graphing y equals log base 3 of x to begin with, I'm first going to find the inverse of that. I'm going to switch this to x equals log base 3 of y. And when you solve that or write it in exponential form, you have y equals 3 to the x power. So let's do a t-table for y equals 3 to the x, just because it's so much easier. Let's plug in values like negative 1, 0, and 1. When you do, 3 to the negative 1 is a third, 3 to the 0 is 1, and 3 to the first is 3. However, we don't want to graph that. We're wanting to graph this, which is the inverse of this function that I just found the t-table for. So to actually graph y equals log base 3 of x, instead of plotting the point negative 1, 1/3, I'd plot the point 1/3, negative 1. I'd flip-flop those x's and y's back, 1, 0, and 3, 1. So let's plot those points on my graph and take a look at what the graph's going to look like. And there is the graph of your logarithmic function. Let's talk about the domain and range. Notice you do have that vertical asymptote line at x equals 0. So let's go ahead and start with that. So that means our domain, we do have domain restrictions here. And here's the rule. You cannot take the logarithm of a negative. You can't take the logarithm of 0. And you can see that on this graph. Your domain is from 0 to infinity. Your range, however, we're going down forever. We're going up forever. So therefore, my range is all values. Why? Because think about its inverse. Here was its inverse. What was the domain and when we did y equals 3 to the x? The domain was negative to positive infinity. The range was 0 to infinity. Notice that they are flip-flop now. The x-intercept here is right here at 1, 0, which again is flip-flops of our exponential graph, which had an x-intercept at 0, 1. Our increasing interval, moving from left to right, our function is always increasing. However, we're going to put from 0 to infinity because my graph does not exist to the left of 0. My decreasing interval, this does not increase. Next up, my end behavior. As we go to the right on my graph goes uphill. And then we're not approaching negative infinity because we can't, because we can only approach 0 because we don't go any further to the left of that. So as we approach 0, my graph does extend downwards forever. Next up, we're graphing y equals log base 1/2 of x. So the inverse of that would be y equals 1/2 to the x power. And we can look at, here's another way you can graph it. You could actually just plot those points. 1/2 to the x, that'd be 1/2 to the 0 is 1. 1/2 to the first power is a half. 1/2 to the second is a fourth. 1/2 to the -1 is 2. 1/2 to the -2 is 4. 1/2 to the -3 is 8. So there's that function. However, we're wanting to graph the inverse of that. So I'm going to do it in a different color. So instead of 0, 1, we're going to graph the point 1, 0. Instead of 1, 1/2, we're going to plot the point 1/2, 1, which is right here. Instead of, this was the point -1, -1, 2. So we're going to plot 2, -1, which is right there now. Instead of -2, 4, which is right here, we're going to plot the point 1, 2, 3, 4, -2. So you're just inverting each and every one of these points is all we're doing. This is, the original graph was an exponential decay graph, but just, again, take those same points that were on your original graph, invert them, switch your x's and y's back, and here's what you're going to get. And there is your inverted graph. Now you could graph the original y equals 1/2 to the x, and you can see they are inverses. Your domain here is still from 0 to infinity. Because the original, well, let's go ahead and do range. Range is from -infinity up to positive infinity. It goes down and up forever. Now, if you were to look at the domain and range of this, it's the exact same two things except for flip-flopped. Your x-intercept is again at 1, 0. Your asymptote line is the y-axis, which is x equals 0. You're increasing nowhere because your graph goes downhill forever, and it goes downhill from 0 to infinity. And the reason why is because its inverse was a exponential decay example. My end behavior, as we travel to the right, my graph goes downhill, so y approaches -infinity. As we travel to the left, as we get closer to 0 on my x-axis, my graph shoots up to positive infinity. Next problem. Y equals natural log of x. Now the inverse of that, or again, we can now, if you would like to, you can just graph this. If you just want to use a calculator and type in some x and y values, you don't have to use inverses to graph it. We could plug some values here, -2, -1, 0, 1, and 2. When you plug those in, and this will be very easy to do, natural log of -2 is undefined. Natural log of -1 is undefined. Natural log of 0 is undefined. So we're going to have to find some better values first off, because none of those values would work. So be careful what you're plugging in. Maybe you should plug in like 1/2, 1/4. You could plug in 3. Here's the values you'll get. So here's a look at our table, and there's a look at our graph. And again, it's pretty easy just to go ahead and plug in some x values since you have your calculator there. Domain of this graph, again, you have the asymptote line at x equals 0 because you can't take the log of 0, you can't take the log of a negative. Therefore, your domain is going to be from 0 to infinity. Your range is still from negative up to positive infinity. You have an x-intercept at the exact same 1, 0. And again, the reason for that is because the inverse would have a y-intercept at 0, 1. Your increasing interval, it increases the entire life of the graph, and that would be from 0 to infinity. Therefore, it never decreases. The end behavior, as we travel to the right on our graph is going uphill, so y would approach infinity. As we travel to closer and closer to 0, moving to the left, our y value goes down to a negative infinity. Next up, we're graphing y equals log base 1/3 of x and then plus 1. Now, I'm not a big fan of how they wrote this because you've got to be careful. This is not what you're doing. The x plus 1 is not what you're taking the log of. It's the log base 1/3 of just the x, and then you're going to add 1 to that answer. That plus 1, this is a vertical translation. That's going to move your logarithm function up 1 unit. So you can actually find log base 1/3 of x, and then add 1 to all the values. And again, you can graph this by using inverses. Again, I'm just going to graph it by using, we're just going to plug in some values. We're just going to plug some x values in. And if you're careful which x values that you plug in, it makes this a little bit easier. But I am going to show you, if you're not careful, how do you find log base 1/3 of x? If you remember your change of base formula, it says you can do the log of x divided by the log of 1/3. You can type it into your calculator like that. And then once you find that answer, like if we plug in 9 for x, you'll do the log of 9 divided by the log of 1/3. Once you find that answer, don't forget to add your 1 to the answer. Okay, so again, I'm gonna use values that are actually multiples of maybe 9, 3, or 9, so that because I've got to say 1/3 to what power is equal to this. And I know I can raise 1/3 to a power that will give me values like, well, it can't take the log of a negative, but values like 3, 9, 27, which won't fit on my graph, but I could use that. And I also know that I can take the log of 1 as an extremely easy value. Okay, so let's plug these in for our x values and let's see what we get for our y's. Okay, there's what I get, and there's my graph. Now, if you remember transformations, again, this +1 right here is only going to take that logarithmic function and move it up a unit. So this right here, which used to be my x-intercept, got moved up to here. Okay, so I'll have a new x-intercept. However, my domain is still the same. I just moved it up 1. My domain is still from 0 to infinity because I've got that asymptote line at x equals 0. My range values, however, goes from negative infinity up to positive infinity. The x-intercept is now moved to here, which is 3, 0. My increasing interval, there is no increasing in this graph. My decrease for the entire life of the graph, which is from 0 to infinity, the whole domain. And then finally, my end behavior. As we travel to the right on my graph goes down forever. As we travel closer to 0, my graph goes up forever. Next problem. Now this is another transformation. You actually have a couple of transformations here from the original log base 2 of x. Again, I am just going to plug some values in. Be careful because if you're moved to the 2, normally I can't plug in zeros and negatives. You can't take the log of 0, can't take the log of a negative. Well, if you plug in a 2 right here, you're taking the log of 0, which you cannot do. What this -2 actually did, if you remember your transformations, normally your asymptote line is x equals 0. However, when you do the -2 on the x, that's going to move that whole graph to the right 2 units. Your asymptote line is now going to be over here at x equals 2. So you're not going to be able to plug in any values to the left of 2. And if you don't believe me, you can try it. However, what I'm going to do is I'll go ahead and put the 2 on my graph just to show you. I'm going to put a 2.5, and we can just say 2.5 there. I'm going to plug in a 2.75. I'm going to plug in a 3, a 4, and a 5. And the way we're going to do that, to type this into your calculator, you'll do, since it's a log base 2 of x minus 2, you'll type it in as the log of x minus 2, whatever you're plugging in for the x, divided by the log of 2, and then don't forget to take the minus of it afterwards. As you plug them in, here's what you're going to get. Okay, that's what I got there. Notice again, I can't plug in 2. I get an undefined value because, again, you can't take the log of 0. So when you do 2 minus 2, it gives you the log of 0. When you plug in 2.5, it gives you 1, and so on and so forth. I plotted the points. Again, you have a new asymptote line that has been shifted over 2 units. So x equals 2 is your asymptote, so therefore your domain is from 2 to infinity. Your range extends down and up forever. Your x-intercept is now here. It was on your table of values located at 3, 0. Your increasing interval, it does not increase anywhere because it decreases the entire life of the graph, which is from 2 to infinity now. Finally, the end behavior. As we travel to the right on my graph goes downhill to negative infinity. Then as we get closer to 2, which is where the graph starts, my graph goes forever uphill, so positive infinity. The next one. Y equals log base 4 of x plus 5 minus 2. Now, let's graph this one a little bit different. Let's actually use some transformations to graph this. Let's forget about the 2 transformations here because they're simple, basic transformations. And let's graph, let me do me a table. Let's plug in some x values and actually just graph log base 4 of x. So you're saying when you're doing log base 4 of x, let's again talk about that. You're saying 4 to what power is x? So you can actually say 4 to the first power is 4, so 4 is going to be an easy one. I know 1 will be an easy one. 16 will be an easy one to plug in. And then you can plug in some more like 1/4 or 1/16. Those are going to be values that's super easy to plug in. And the reason, again, why is log base 4 of 4 says 4 to what power is 4? That's 1. Log base 4 of 1, when you plug that in, log base 4 of 1 is 4 to what power is 1. Log base 4 of 16 is 4 to what power is 16. 4 to what power is 1/4. 4 to what power is 1/16. And you can plot those values, but however, what we're trying to graph has been translated. It's that graph that's been shifted. So what I'm going to do, I'm actually just going to do me a new column in my t-table. And we are going to graph log base 4 of x plus 5 and then minus 2. And what that's going to do is that's going to be a new x and y. This plus 5 right here is going to shift our whole graph left 5 units. So all my x values are going to move left 5. So here's your new x values. 4 minus 5 would be -1. 1 minus 5 would be -4, and do the same thing for all those. And then all my y values, this is a transformation down 2 units. So all my y values, I'm going to take here and just move them down 2. I'll have -1, -2, and so on and so forth. And there is my new graph. So I just use my transformations, plot those points, and that's what your graph is going to look like. And let's go ahead and plot those and connect our dots. And there's your graph. Notice the asymptote line looks like it's right here now. And the reason it's over here at x equals -5 is because once again your graph got shifted left 5 units. So therefore your domain is going to be from -5 forever. Your range extends forever down and up. Your x-intercept looks like it's somewhere right over in here. Now to find our x-intercept, well, it's right here on my graph. It's right there actually. It's located at 11, 0. Your increasing interval, your graph increases for the entirety of the entire graph and it never decreases. And then your end behavior. As we travel to the right on my graph is going uphill, so my y value approaches positive infinity. As we get closer to 5, my graph shoots down, so my y value approaches negative infinity. Next graph. Now, another method we could use for this is we can graph this by using Desmos. So let's try that out. Now, the way that you would graph it, now notice the negative here that's going to flip it across your x-axis or y-axis. Actually, it's going to flip it horizontally. So your whole graph should be located over here now because of that flip. But the way you're going to have to type this in, this would be the log of -x, and you might be saying, I didn't think we could take the log of a negative. You're going to have to plug in negative values for x in order to allow this to be legal. If you were to plug in 1, you're right, that's the log of -1, but if you were to plug in -1, it would be legal. We're going to type it in as the log of -x divided by the log of 1/2, that's your change of base formula, and then plus 3. So here's where I typed it in, y equals the log of -x over the log of 1/2 plus 3. And here's another nice feature of Desmos. If you wanted to transfer this graph over, which you can see what the graph looks like there, if you wanted, and you see your vertical asymptote line there at 0, by the way. Another way that you can transfer this over if you need some points is you can actually click on this right here, the edit list. You can click on convert to table and it actually does a t-table for you. And you can type in and plug in any values you want. You see here -2 and -1 plugged in. If you want to come down here and hit, let me come right here, hit enter, and you can plug in a -3, enter, whoops, let me delete that, hit enter. You can plug in a -4, hit enter, plug in a -5, hit enter. You can plug in any values you want to, and then just transfer these straight to your graph. And that's what I've done here. Let's go ahead and label everything. Our domain is now actually from -infinity up to 0. Make sure that you always start from the lowest value up to the highest value. Your range extends downwards and upwards forever. Your your x-intercept actually was right here at a -8, 0. And it's, again, using Desmos, it's very easy to see. You just click on it right here. There is your x-intercept. Your asymptote line is going to be the y-axis, which is at x equals 0. You're increasing forever on your graph, which would be from -infinity up to that 0, and you're never decreasing. And then finally, your end behaviors. I'm going to do the -infinity first. As you approach -infinity, or as you go to the left, your graph is going down. And then as you go to the right on your graph, as you get closer and closer to 0, your graph goes up to positive infinity. Okay, moving on to the next problem. Number 8. Y equals 3 times the natural log of x minus 1. And we're actually going to use Desmos for this again. And before I do, let me show you once again on that last problem where I found the log at whenever you're ready to graph these. It's over here in the functions menu, and I told you something, actually a little lie. I told you had to do the change the base formula, but I only did that to remind you how to use it. You actually have log base a function right here, and you could type in any base that you wanted to. Like that last one was a base 1/2. So you could actually type in log base 1/2 there. Whoops, let's try that again. Or you could type it in as log base 0.5, but you can type that base in down there. You don't have to do all this work. However, the one that we're on is a natural log, so we're going to find that exact same natural log function in the same place. So let me go ahead and graph that. And there it is. And now let's once again talk about the way they wrote this is kind of deceiving. This is wrong. If you don't have the parentheses around it, we're going to assume that only the natural log of x is what we're taking. We're not taking the natural log of the entire function. So this is, now what's the difference in that? If you think transformations, that's a horizontal transformation. What we're dealing with is actually a vertical transformation. It's going to carry our function down 1. So here is a look at what that function is going to look like. Let me go ahead and close that. Whoops. So there's our function, and let me go ahead and you can zoom in, zoom out, or whatever. Looks just like the other ones. Let's transfer that graph over to our graph, and there is that graph. Let's go ahead and do all of our specs here. Our asymptote line I like to start with is x equals 0 because you're going to need that asymptote line to find your domain, which is 0 to infinity. Again, you cannot take the log or natural log of 0 or a negative. That's the reason why. -infinity to infinity is your range. Your x-intercept is going to be right here. And to find that x-intercept, we're going to go back to Desmos, and we're going to zoom in, and you can see that it crosses at a weird spot, but we can just click on it right there. So 1.396. So our x-intercept is about 1.4. Increasing interval, we're constantly increasing over the life of the graph, so therefore we're never decreasing. And finally, our end behavior, as we go to the right on our graph goes uphill, and as we approach 0, our graph goes downhill.